Welcome to Lecture 17 of CS 182. Today, we're going to talk about generative modeling. So far in this course, we've discussed supervised learning, and before the break, we also discussed reinforcement learning. Starting today, we're going to talk about unsupervised learning. But before we do that, we need to discuss a little bit about probabilistic models. Virtually all models that we learn in this course and other machine learning courses are essentially probabilistic models. You could imagine that one of the simplest kinds of probabilistic models is a model that learns a distribution over some random variable x. For example, if you have a collection of points in 2 dimensions and you estimate the mean and covariance of those points, what you're really doing is you're learning a multivariate normal probabilistic model of those points. And sometimes we draw it as an ellipse like this, where the contour of the ellipse represents 1 or 2 standard deviations from the mean. Right? So this way you can imagine the mean is at the center of that ellipse, and 1 or 2 standard deviations is where the line is. In this case, it's probably 2 standard deviations. We can also have conditional probabilistic models, and these are the ones that we spent so much time learning about in this course so far. So these are models that represent a distribution P of y given x. And of course, things like linear regression fall into this category, where y represents the vertical position of the points and x represents the horizontal position. But also deep neural network classifiers fall into this category, where y represents the label and x represents the image. So far in this course, we've mostly talked about learning conditional models of the form y given x. Today, we're going to talk about learning P of x. Now, why would we want to do this? It's clear why we want an image classifier. Why do we want to learn the distribution over images or other kinds of inputs? We'll come back to this point shortly. The thing is, we've already seen some generative models, we just didn't describe them as such. So the kind of simple textbook picture of a probabilistic model or generative model is this P of x. Why does it call the generative model, by the way? Well, it's called the generative model because it can generate x's. And you can't generate an x from a P of y given x model, so a linear regression model won't help you generate x coordinates. But if you have a multivariate normal distribution over these 2-dimensional random variables, you can generate new 2-dimensional random variables from the same distribution by sampling them from P of x. So let's say we have a multivariate normal, right? The kind of generative model that we already learned about is very different from this multivariate normal, but it really fundamentally solves the same problem, and that's the language model. So the language model also represents a P of x, where x is a sequence of words. They're just different ways to solve the same problem. Now, the language model is a very different representation of P of x than the multivariate normal, but it's solving the same problem in the sense that it is also representing a probability distribution, in this case, over sentences. Representing a probability distribution means that it can assign a probability to every point in that space. The space for a language model is the space of sentences. And for every possible sentence, the language model can assign a probability. It does so by using, in this case, the chain rule of probability. Right? If you recall, the chain rule says that any joint distribution can be factorized as a product of conditional distributions. So if we say that P of x is really P of x1, x0, comma x1, comma x2, comma x3, etc., 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 comma x6, you can write it by the chain rule of probability as P of x0 times P of x1 given x0 times P of x2 given x0 through 1 times P of x3 given x0 through 2 times P of x4 given x0 through 3 times P of x5 given x0 through 4 times P of x6 given x0 through 5. Now, those of you that are listening carefully will have noticed that there is a little discrepancy between what I said and what appears in this slide. I said that you start with P of x0, but on the slide the equation actually starts with P of x1 given x0. So this might seem a little bit off, but it's not. What is x0? Well, x0 for the language model is the very first token that we feed in at the beginning. And the first token is always the same. It's always the start token. So it's not actually a random variable. We know what the start token is. It's not random. It's always the same. So that means that in reality, you can omit the dependence on x0 in each of these conditionals because x0 is not a variable. It's just a constant. Right? So that means that you can equivalently write it like this, and now it's much more obvious that the language model really is learning a joint distribution over x. It is not a conditional distribution. It's not conditional on x0 because x0 is not a variable. It's really a full joint, and it is a probabilistic model. It is a generative model in the same exact way that the multivariate normal distribution up above is a generative model. It's just that a language model represents a much more complex distribution over a much more complex object, namely natural language sentences. But it satisfies all the requirements for a probabilistic generative model. It can assign a probability to every sentence that you give it. You can use it to sample sentences. You can actually feed in the start token, get a softmax distribution over the first word, sample from it, feed it in as a second word, and so on. You can actually generate a natural language sentence from this distribution. So it is a full-fledged probabilistic generative model. Okay, now why would we want to do this? Well, we already learned about a few reasons why we might want language models. So, for instance, you can train your language model on large amounts of data that does not have any labels. So you could download all of Wikipedia and train a language model. You could use it to acquire representations, which are very well suited for downstream, in this case, natural language tasks. This is what we learned about when we talked about Elmo and Bert. And you can pre-train it for later fine-tuning, as we talked about when we discussed Bert. And of course, you can use it to actually generate things. So if you actually want to complete some sentences or generate fake sentences, you can use a language model. So the topic of discussion today is not how to model language. We've already talked about that. The topic is how do we go from language modeling to everything modeling, right? Can we use the same idea that we use to build these language models to build models of other types of objects, like images or sounds? This is called unsupervised learning. It's called unsupervised learning because the training data that is provided to the model is not labeled with any labels. It does not require supervision. It just requires unlabeled data. And just like language models can be used to acquire representations, or models that can later be fine-tuned to other tasks, or for actually generating things, generative models that we build on other types of data, like images, sounds, and so on, can also be used for representation learning. They can be used for pre-training for later fine-tuning, and they can be used to generate things. And just like language models, generative models on images and other types of data do not require supervision, which is why we call them unsupervised learning. Okay, so can we language model images? So let's say that we're going to be given some real images. We'll use them for training, and then there's some new set of test images. Let's say we haven't seen these images before, and a particular task we might want to do is complete those images. We can also generate entirely new ones, but maybe the particular task we can think of is completing an image. So maybe there's a real picture of this dog in the middle and the bottom part is cut off, and you want your model to complete the bottom part. Okay, so if you can somehow train an image language model on images, you can ask it to fill in the blanks in the same way that a language model can complete a sentence. So before, each time step for the model was a word. Now every time step will be a pixel. Okay, so we are literally going to be trying to train a language model over pixels. So just like before, we're going to apply the chain rule of probability to factorize the distribution p of x as p of x1 times p of x2 given x1 times p of x3 given x1 through 2, etc., 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 where the subscript denotes which pixel we're looking at. So x is an array of pixels. x1 is the first pixel, x2 is the second pixel, x3 is the third pixel, and so on and so on and so on. Now, we do have to pick an ordering over pixels to do this. So we're going to pick some fairly arbitrary ordering, and we'll discuss that in a second. But then the way that the model will work, a very simple kind of RNN model, will be exactly the same as the language model. So we have some kind of start token, we pass that in, and then instead of producing a word, what we produce is a pixel. We discretize a set of pixels. Colors are actually discrete. Each color channel takes on a value between 0 and 255, so there are only 256 possible values. So we just have a big softmax over possible color values, and we produce them one at a time. So at the first time step, the RNN is fed in the start token, and it produces a softmax over the color of the first pixel. And then, just like in a language model, at test time, that generated sampled color is fed in as input at the second time step, and it generates the color of the second pixel. And then this process repeats. Okay? Now, of course, there are a great many pixels in each image, so this will be a pretty long sequence. And we do have to pick an order. So in this case, the particular order I picked is a scanline ordering. So you first go through the first row of pixels, x11, x12, x13, then if this was a 3x3 image, then you go to x21, x22, x23, then you go to x31, x32, x33. So that's one particular ordering. And you could pick any other ordering. It's, there's not a single really great choice, but it's nice to pick an ordering that has some amount of locality. So the scanline ordering is nice because, at least horizontally, nearby pixels are sequential, although vertically they are not. All right. So this is basically the main idea behind something called pixel RNN or pixel CNN. But there are still some details we need to figure out to turn this into a full-fledged generative model. First, we have to decide how to order the pixels. Unfortunately, there isn't really like a great perfect answer, so we just pick something. We have to decide what kind of model to use. So when we talked about language modeling, we learned about RNNs, LSTMs, multi-layer LSTMs, bidirectional LSTMs, transformers, and of course, many of those choices are also available to us when we are building these models over pixels, and so on. Okay, so the main principles for training these, and these are called autoregressive generative models, are that 1, we divide up x into its dimensions, x1 through xn. So x might be an image, whereas x1, x2, and x3 might be different pixels in that image. Step 2, we discretize each of these dimensions into k values. Now, in some cases, like for example, when we're generating images, the image pixels are naturally discretized into, for example, 256 values, because pixels can only take on 256 different colors. And then step 3, we represent the full joint over all the pixels or over all the dimensions of x, whatever x might be, via the chain rule. And that's the equation that we saw before. So when we use the chain rule like this, every dimension depends on all previous dimensions. And that dependency on all previous dimensions is captured by an RNN or by a transformer with masked self-attention. And then the actual distribution over each dimension is just a softmax over the k possible values that it could take on. And then step 4, use your favorite sequence model to actually model this p of x. It could be an RNN, an LSTM, a stacked LSTM, a bidirectional LSTM, a transformer with masked self-attention, whatever you want. Okay, now let's say that you train this thing. How could you use an autoregressive generative model? Well, you can sample from the autoregressive generative model so that you can do using ancestral sampling. So you first sample x1, then you sample x2 given x1, then you sample x3 given x1 through 2, and so on. And that's done exactly the same way as generating a sentence from a language model. So we've already learned how to do that. That's actually quite straightforward. If you want to refresh on that, go back to the Seek to Seek lecture from before spring break where we explain the sampling process. You can use it for completion. So if part of the image or whatever data type you have is known and you want to complete the rest, you can feed in the known values. So you don't sample the known values, you just feed in their known values in there and then sample the rest. And that's also a perfectly legitimate thing to do. In fact, if you want to sample randomly, then it's straightforward. If you want to find the most likely completion, then you can use beam search, just like we used beam search for things like machine translation. And of course, you can use them for representations. And here again, the idea is the same as with something like Elmo or BERT. So both of those were sequence models that were used for representation learning, and we can also use sequence models for representation learning on images, where we would take something like the hidden state of the RNN as the representation of pixels to use for downstream tasks. Okay, so let's walk through one popular class of models in this category that is specific to autoregressive generative modeling of images. And this is called the pixel RNN. If you want to learn more about the pixel RNN, I have a citation to the paper at the bottom of this slide. So the idea in pixel RNN is that we're going to generate the pixels one at a time, left to right, top to bottom, in scanline order. So the probability of the whole image is given by the product over all the pixels. If it's an n by n image, there are n squared possible pixels, and each pixel depends on its predecessors, which are defined as all preceding scan lines and all preceding pixels to the left of the current pixel in the current scan line. Now each pixel consists of 3 color channels, so we also have to generate 1 color channel at a time. So there's actually a small network for every pixel that generates the red color given all the previous pixels, then the green color given all previous pixels and this pixel's own red color, and then it generates the blue color given all previous pixels and this pixel's red and green color. You could also just treat this as 3 separate pixels if you like, but they special case it and have a little length 3 kind of second dimension to their autoregressive model. And then every color channel is a 256-way softmax. So every color channel's brightness can take on 256 possible values, which is how many possible pixel brightnesses there are in 32-bit color. So with this model, once you've trained it, you can give it, for instance, the top half of an image, and it can complete different random realizations for the bottom half. And these are actual samples generated by the pixel RNN when it was presented with the top half of each of these images. And you can see that the completions are varied because they are being randomly sampled, but they're also fairly sensible. So, for instance, that picture of a dog is completed with different dog-like bottom halves, and maybe it doesn't know how big the dog is, so sometimes the dog is tiny, sometimes the dog is huge, because it's not sure. The picture of what looks like a person swimming is also completed in various ways. Sometimes the person is swimming, sometimes they're actually seemingly riding in a canoe or kayak. Okay, so it's sampling meaningful possible completions for this image. Some practical considerations with pixel RNN. First, it is quite slow, right? Because while the basic recipe is the same as a language model, if the, let's say that the image is 32 by 32 pixels, that means that there are about 1,000 pixels in that image. So that would be like a sentence with 1,000 words. And each pixel itself has 3 color channels, so that raises it to 3,000. Now that is quite a lot. So both training the pixel RNN and sampling from it can be quite expensive computationally, even for very small images like 32 by 32 images. Generating the image row by row like this might fail to capture some of the spatial context that is present in images. Because the pixels that are located right above in the scan line are considered to be far away in the RNN ordering. So even though the pixel right above xi should be very similar to it because of spatial coherence, in a 32 by 32 image it would be 32 steps away. So the RNN might struggle to remember what was going on. And there are various tricks that we can use in practice to mitigate this issue with pixel RNNs. And there are also many practical improvements and better architectures that are possible to improve pixel RNN further. So one example that is described in the pixel RNN paper is a kind of, is what they call the diagonal bi-LSTM, diagonal bidirectional LSTM, where actually the current pixel receives input from its predecessors in scanline order, but it also has connections from the scanline right above it. And that's pretty straightforward to do, right? Because you can short circuit the connection from any previous hidden state, right? So you don't have to go in order. You can basically create a shortcut connection from the hidden states that were right above, even though they're many time steps ago. So I'm not going to go into detail about the diagonal bi-LSTM. If you want to get more details about it, I would encourage you to check out the paper. One idea that's also described in pixel RNN is a simplified model called pixel CNN. And I want to describe this simplified model both because it's a lot more efficient and because it illustrates some possible simplifications we can make to these types of autoregressive models. So the idea in the pixel CNN is to make this generation process much faster by not building a full RNN over all pixels, but just using a convolution to determine the value of a pixel based on its neighborhood. And I should also mention that this idea is not mutually exclusive with building an RNN. You can actually combine them together. But let me just explain the pixel CNN idea on its own. So before, we would build an RNN that would read in all the pixels that were above and to the left of the current pixel. Now what we're going to do instead is we're going to say, well, the value of this pixel that we're going to generate, this 256-way softmax, is only going to depend on a local neighborhood of this pixel. That's very much like how a convnet works. Except the problem we have is that we haven't generated the whole neighborhood. If we're going to generate these pixels one at a time in scanline order, the pixels above the current pixel and the pixels to the left have been generated, but the pixels below and the pixels to the right have not been generated yet. So what we're going to do is we're going to actually have a masked convolutional neural network that's going to read in the values of the pixels, but it's going to have a weight of 0 on everything that is below and to the right. So the value that this convnet generates is going to depend only on the pixels that are to the left and above the current one. It will not read in the current pixel because it's generating it, and it will not read in anything below or to the right. So the current pixel is masked out, and the ones below and to the right are masked out because they haven't been generated yet. And that just means that in the corresponding convolutional filter, their weights are just forced to 0. But the pixels above and to the left are read in, and you have a convolutional network with stride of 1 with no padding, or rather with 0 padding, so that it doesn't reduce the resolution of the image, and it will actually generate at the end a 256-way softmax. So you can think of it as a fully convolutional network that doesn't reduce resolution. And that will generate a value for this pixel, and it will be very fast. Can we parallelize this process? The answer is actually yes. So parallelizing the RNN over all the pixels in the image is of course impossible because the RNN needs to read in those pixels one at a time. But the convnet can actually be parallelized, at least during training, because during training you have all the pixels available to you, so you can train all of them in parallel, provided that you force the masking to remain. So you have to force the filter to have weights of 0 on everything that is at that pixel below or to the right. And then you can do parallelized training very fast, the same way that you train regular convnets. Can you parallelize this process during generation, when you want to generate a new image? Take a moment to think about this question. So the answer is no. You can't actually parallelize generation with a pixel CNN because parallelizing generation of their pixels means that you would have to generate a pixel that is in the middle of the image at the same time as the top left. But for the pixel in the middle, it needs to read in the pixels above and to the left of it to figure out its value, and those haven't been generated yet. So generation still needs to happen one pixel at a time, just like in the pixel RNN, but training can be entirely in parallel. But this is also why the pixel CNN is not as restrictive as it seems. Because at first it might seem like the pixel CNN is a bad idea because the value of that pixel in the middle only depends on a small neighborhood. But the thing to remember is that the pixels in that local neighborhood themselves depend on the values in their neighborhood. So, for example, this pixel that I've highlighted with the arrow is outside of the 3x3 kernel that we use to generate xi, but because the pixel up and to the left of xi depends on that point, xi also depends on it, just indirectly. And because the pixels will be generated one at a time, they will in fact actually be consistent in this way. Now, of course, in reality, we can do pixel CNN with multiple layers of convolutions and larger receptive fields. So if you have, let's say, 5x5 convolutions, and you have multiple layers, maybe you have 5 or 10 layers, and you have a small 32x32 image, the receptive field might include almost the entire image. So the picture that I have here on the slide is a little bit deceptive. In reality, the receptive field for a pixel CNN at every point is not just a little 3x3 neighborhood. It might be even as big as the whole image, but even if it isn't, the pixels outside of that receptive field still affect the value of xi because they affect other nearby pixels, which themselves determine the value of xi. So even though this seems like a somewhat restrictive architecture, it's actually quite powerful, and it is much, much faster during training. Okay. Now, we can also build other kinds of models, very much the same way that we discussed in the language modeling portion of the class, not just RNNs. And we could, for example, build a pixel transformer. So we could go from having a pixel by pixel LSTM or stacked LSTM to having masked self-attention and position-wise nonlinear networks repeated n times, just like in the transformer decode. So we can use a transformer decoder style architecture to build a model over images. So if you want to learn more about this, check out the paper by Parmar et al. Called Image Transformer from 2018. Now, the image transformer does have some very nice properties when we talk about pixels, because the transformer does not actually impose a particular ordering. In fact, that's why we need things like position encodings, because without position encodings, it doesn't even have any knowledge of where the pixels are. So that means that even though we have to pick an ordering to generate the pixels, all the pixels are in some sense equally close to each other. So the pixel right above xi is very far away from xi if we're using an RNN in scanline order, but all pixels are equally close for self-attention. So self-attention can just as easily index into the pixel immediately to the left of xi as it can index into a pixel immediately above it, or for that matter, a pixel in the top left corner. So self-attention is a really good choice for something like this, because even though we still have to pick an ordering for generation, that ordering does not affect how easy it is to communicate information from one pixel to another, because with self-attention, they are all equally close. There is, however, a problem with this recipe, which is that the number of pixels can be very large. And attention can become prohibitively expensive in this case. Remember that the runtime for an attention model is O of h squared if the horizon is h. So if you have h time steps, then it costs you O of h squared in general to compute self-attention. For short sequences, we actually don't worry about this because the cost of that h squared attention calculation is comparatively lower than the cost of running all of the position-wise nonlinear networks and things like that. So it's basically big, in the big O sense, it's quadratic, but it has a small coefficient in front of it. What that means is that for small values of sequence length, the quadratic part doesn't bother you. But of course, if the sequence gets long enough, eventually it becomes problematic. Eventually, a quadratic term will always overpower anything that is linear. So the idea that is actually used in image transformers to make this computationally feasible is to only compute attention for pixels that are not too far away. So the intuition here is similar to the pixel CNN, that the local context of pixels is more important than very distant pixels. So the image transformer actually uses a modified masked self-attention, where the mask prevents the model from looking at pixels that have not been generated yet, but it also prevents it from looking at pixels that are too far away. So there are two kinds of localities that are used. One is a local 1D attention on the left, and the other one is a local 2D attention on the right. So in 1D attention, it looks at just the pixels to the left of the current one in the current scan line, and in 2D attention, it looks at a neighborhood to the left and above, but not all the way back to the top left corner. So this makes it look a little more like pixel CNN, but with self-attention. And for larger images, this can be very important. For smaller images, it might not matter as much. Okay. Now we can look at the kind of generations that we can get from pixel RNNs versus transformers. So the images on the left show generations by sampling from pixel RNN after training on CFAR10. The images on the right show samples from the pixel transformer, from the image transformer, when trained on CFAR10. And you can see that the transformer seems to generate pictures that look, a bit more like realistic things. They're still not perfect, but they look a bit more like cars and birds and things like that. Whereas the pixel RNN images, if you stand really far away from the screen and you squint a little bit, they kind of look like pictures, but not terribly realistic pictures. Okay, now one more thing I want to mention about these types of models is conditional autoregressive models. Conditional autoregressive models. So what if we want to generate something that is conditioned on another piece of information? Well, much in the same way that we could train conditional language models, we can train conditional autoregressive models. For example, we could generate images of specific types of objects. For instance, you can have a model that doesn't just generate random pixel images, but you can tell it generate a bird, generate a car, generate a steam train. You could have a conditional autoregressive model for imitation learning that generates distributions over actions for imitation learning conditioned on the observation, right? That's another example of a conditional autoregressive model, which I mentioned in the imitation learning lecture. And there are, of course, many other examples. The recipe is very similar to a conditional language model. So you have something that you're conditioning on, which we would call a context. This could be as simple as an object label or as complex as the state or observation in imitation learning. The context is processed using some kind of encoder network, which could be just a feed-forward model, a convnet, or it could be another RNN, and that is used to start the first time step of the autoregressive generative model. So this is just like conditional language models. The encoder could be extremely simple if, for example, you're generating images of a class, so the context is just a one-hot vector representing which class to generate, or it can be very complex. For example, if you have a multimodal policy in imitation learning, the encoder is actually representing the policy, and the RNN over the different dimensions of the action space might actually be a fairly small RNN that just generates the individual dimensions. So here are some example images for a conditional autoregressive model. In this case, this is a model that is conditioned on an object class. Classes here are things like African elephant, coral reef, lawnmower, etc. And you can see that for each object class, it generates pictures that are maybe a little bit more evocative of that class. These images also look substantially better than the purely unconditioned pixel RNN examples that I had a couple slides ago. Okay, so some trade-offs and considerations for autoregressive generative models. Autoregressive generative models are basically like language models, but for other types of data. Although it's more accurate to say that language models are just a special type of autoregressive generative model. So the notion of an autoregressive generative model is actually more general than a language model. You can represent autoregressive models in many different ways. You can represent them with RNNs or LSTMs. You can use local context models like pixel CNNs, which are cheaper to train and simpler. Or you can use more complex self-attention models like transformers. There are some interesting trade-offs for these models compared to other models we'll talk about later. And I realize this is like a little weird because I haven't described the other models, but just as a preview, here are the trade-offs that we'll find. Generally, one really good thing about these kinds of autoregressive generative models is that they provide full distributions with probabilities. So they really will assign a probability to every possible x, and those probabilities are easy to get. That is not going to be the case for some of the other more complex generative models that we'll talk about on Wednesday. They are conceptually very simple. If you understand language models, chances are you're going to understand autoregressive generative models. Some of the other types of models we'll discuss are more complex. The downside is that they can be very slow for large X's, for example, high-resolution images. They are extremely slow to train, and they are extremely slow to generate. Because of this, generally you need a limited image resolution. So when we talk about things like generative adversarial networks or GANs later, probably next week, we'll talk about generating images that are HD resolution, 1024 by 1024. Whereas for these pixel RNNs, 32 by 32 or maybe 64 by 64 is about the max you can get. So resolution tends to be really limited because of this computational cost.